Hello students, good afternoon. Welcome to the chemistry class. Today in this class we will discuss about the second part of the chapter chemical kinetics. Today in this portion we will discuss about the dependence dependence of reaction rate on concentration of reactants. Okay, so in this portion we will discuss firstly law of mass action. Law of mass action. So the quantitative dependence of reaction rate on the concentration of the reactant was first studied by Goldberg and Wage in 1846. So according to them, the law of mass action can be stated as follows: at constant temperature, the rate of chemical reaction is directly proportional to the product of active masses of the reacting species, with each active mass term raised to the power equal to the stoichiometric coefficient of that species in a chemical reaction. Means at constant temperature, the rate of a chemical reaction will be directly proportional to the product of active mass, and their stoichiometric coefficients will be raised to the power of that active masses of the reactant. Okay, so it may be recalled that stoichiometric coefficients are the numerical coefficients on the species present in the chemical equation. Let us consider the following simple reaction in which A plus B gives a product. Okay, so according to the law of mass action, rate of reaction directly proportional to the active mass of the reactant A and active mass of the reactant B, or you can write it after removing proportional. There will one constant will come, that is known as the rate constant and denoted by K. So now the rate of reaction will become equal to K active mass of A and active mass of B, where K is the constant of proportionality and known as the rate constant, and square bracket of A and square bracket of B represents the active masses of reactant A and B respectively. Okay, so according to this, for any reaction you can write the law of mass action or rate of the reaction. Let us consider more general reaction expressed in the given below. A plus B plus C gives a product, okay, in which small a, small b and small c are the stoichiometric coefficients of reactant A, B and C. So in this reaction, these are stoichiometric coefficients. Now for this reaction, the rate of reaction will directly proportional to active mass of A की power stoichiometric coefficient small a, B की power small b and C की power small c. Now after removing proportional, there will be a constant, that is rate constant will come. So now the rate of reaction will equal to K A की power small a, active mass of B की power small b and active mass of C की power small c. So in this way you can write a rate of reaction for any reaction will be like that. Okay, so what is the active masses? So the term active mass in the statement of law of mass action indicates that the whole mass of a reactant may be active. Okay, it is the mean of active mass. Okay, so Goldberg and Wage assume that the active mass of substance in a solution or a gas phase is equal to its molar concentration. Okay, so the assumption is valid only for the ideal cases. For the real system, the active masses must be somewhat less than the molar concentration. Therefore, the new term is called activity has been introduced to account for the active masses of the real system. However, in the forthcoming discussion, we shall adopt the assumption of the Goldberg and Wage and will take active masses as equal to the molar concentration. Okay, so active mass basically denotes the molar concentration of the reactant. Okay, so the active mass of molar concentration of a substance can be expressed in the following two units, that is concentration unit. In this unit, the active mass of the substance is represented in terms of number of moles per liter, and second is partial pressure unit. This unit is used for the gaseous substance only, and in this unit the active masses of gaseous substances is represented in terms of its partial pressure. Okay, so these are the basically active masses. Now For an ideal gas equation, PV equals to nRT. Now P equals to n upon V RT. So if temperature is constant, then P will directly proportional to n upon V, means molar concentration. So the active mass of H2 and I2 present in the gaseous mixture and having partial pressures of 0.5 atmosphere each can be expressed as follows. Pressure for hydrogen gas equal to 0.5 and pressure for iodine gas will be equal to 0.5 mole. Okay, so although the law of mass action helped a lot in understanding the dependence of the reaction rate on the concentration. So basically the rate law helps to find out the concentration of a reaction at a prediction sometime differed considerably from the experimental result, and the rate expressed obtained on the basis of the law may not always be agree with the experimental fact. Okay, so for example, let us consider an example. In here you have seen that there is a general reaction, but in here you can say a real example. For example, 2NO plus H2 gives N2 plus H2. So according to law of mass action, rate of reaction will be equal to K active mass of NO की power 2 and active mass of H2 की power 2. So you can write the active mass of a reactant for any of the reaction. Okay, rate of reaction equals to K NO की power 2 and H की power 1. This data will come experimentally. If you examine this equation experimentally, if you watch according to stoichiometric coefficient, then rate constant will come this, but according to experiment, then rate constant will come like this, because in this reaction experimentally the concentration of NO is depends twice, but the concentration of hydrogen will depend on one concentration term only. So the experimental data and theoretical data will be different always. Okay, thus the prediction of law of mass action may or may not be agree with the experimental fact, means the experimental data and the theoretical data every time will not be same. Okay, now rate law and rate constant. So what is rate law? The mathematical expression which describes the experimentally observed dependence of the reaction rate on the molar concentration of the reactant is called the rate law or rate law equation. Okay, so the mathematical expression which describes the experimentally observed dependence of the reaction rate on the molar concentration is basically known as the rate law. So for example, the decomposition of N2O5 gives 2N2O5. Okay, 2N2O5 gives 4NO2 plus O2, and for this the rate law will be rate equals to K N2O2 की power single time, because its concentration depends only one time. Okay, so for a general reaction, the rate of reaction rate will be expressed as a rate equals to K A की power small a and B की power will be small b here. I think there is somewhat mistake. Okay, now there are other examples here for which you can write the rate law. For example, this reaction 2NO plus 2H2, the rate will come. These are the experimental data, because in experimental data I have tell you before that the stoichiometric coefficients never will be equal to the experimental data, they will be differ. So according to this reaction and according to this reaction, the rate will be equal to K NO की power 2 and H2 की power 2, but here the power of H2 is 1, because experimentally when we will see that the concentration of hydrogen will depends only single time of concentration. So here it will be only single, power of single. Okay, so experimental data will be differ. For other reactions you can also watch here the rate of the reactions or rate law. Okay, now rate constant. So rate constant, a specific rate constant What is this? So the rate constant of the reaction is equal to the rate of a reaction when the concentration of each of the reactant is unity. So rate constant of a reaction is equal to the rate of reaction when the concentration of each of the reactant will unity, means for all the reactants the value will be 1. Okay. So for the reaction A, B and C product, rate will be a की power P, Q and R. So P, Q, R equals to small n, which is the sum of the stoichiometric coefficients, and R equals to rate constant, and it is represented in concentration of reactants e power n. So K equals to rate upon concentration of reactant ki power n. Now putting the value of rate and concentration, we will find out the unit of the rate constant. Okay. So the unit of rate constant will be mole per liter per second. Okay. Okay. Thank you. Have a nice day.